Students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as rotational motion. Let's try to find out the moment of inertia of a solid cylinder about its own axis. Let's try to find out moment of inertia of a solid cylinder. First thing we'll do is we'll try to find out the moment of inertia of a cylinder about its own axis. I can say that a cylinder can be considered to be built up of small discs piled one upon the other. A cylinder can be considered to be built up of small discs piled one upon the other. Therefore, I can say that the moment of inertia of the cylinder can be considered as the sum of the moment of inertia of all such discs. Therefore, I can say that moment of inertia of cylinder can be considered to be sum of moment of inertia of all such discs. Right? Do we get this in clear? Now, let's assume that let's draw a cylinder and see how it looks. Let's consider cylinder, right? Let's draw the x and y axis. Say this is my x axis. This is x axis, and let's draw the y axis. Right? This is your y axis. Let this point be O. Right? Let's take a small disc on the cylinder. Set a small disc of the cylinder. Let's assume that this is the axis of that disc, such that the axis of the disc is at a distance of x from the axis of rotation. Right? Let's assume that AB is the axis of the disc. Let's assume that the width of this disc is dx. Right? Let's assume that the radius of the cylinder is r. Right? Now, this is axis of cylindrical symmetry. X axis, or let this be your axis of cylindrical symmetry. Right? Now, we said that I can say that the moment of inertia of a solid cylinder about an axis, moment of inertia of a solid cylinder about an axis passing through the cylindrical symmetry, about an axis passing through cylindrical symmetry. I just showed you what is the axis of cylindrical symmetry. So it is as good as the axis of cylindrical symmetry is the same as the axis of a disc passing through the disc and perpendicular to the disc. A cylinder can be considered as a disc which has very high width, right? So I can say therefore this is going to be the same, is going to be equal to the moment of inertia of a disc, moment of inertia of a disc about an axis passing through the center, about an axis passing through the center and perpendicular to its plane. This is nothing but, if I consider this axis of cylindrical symmetry, it is going to be the same as moment of inertia of a disc passing through the center of the disc and perpendicular to the plane of the disc. Now, if m is the mass and r is the radius of the cylinder, if m is mass and r is radius of cylinder, if m is the mass and r is radius of the cylinder, then I can say that moment of inertia of the cylinder, moment of inertia of the cylinder about its own axis of rotation, its axis of symmetry will be the same as moment of inertia of a disc, which is going to be nothing but half mr square. So this is going to be the moment of inertia of a cylinder about its axis of symmetry. Fine. Now let's find out the moment of inertia about an axis passing through the center and perpendicular to the axis of symmetry. About an axis passing through its center, and perpendicular to its own axis of cylindrical symmetry. Okay, you will say that let's assume that mass of the cylinder is m, radius of the cylinder is r, and length of the cylinder is say l, right? So is the of the cylinder. So m is the mass of the cylinder, r is the radius of the cylinder, l is the length of the cylinder, and it is rotating about an axis. It is rotating about an axis passing through its center and perpendicular to its axis of cylindrical symmetry, perpendicular to its axis of cylindrical symmetry. Fine. Now let's consider, I can say that the cylinder can be imagined to be made up of number of thin discs. The cylinder can be imagined to be made up of or number of thin disc each of radius r and placed adjacent to each other, each of radius r and placed adjacent to each other, right? In that case I can say consider one such elementary disk, consider one such elementary disk of radius r and thickness dx, right? At a distance of x, at a distance of x, at a distance of x from the center of the cylinder, right? In that case I can say what will be the mass of the elementary disk. I can say that the mass of elementary disk, total mass is m, which has been divided into length L. So this will be my mass per unit length multiplied by the length of the disk. That will be my mass of the elementary disk. Total mass m has been divided in length L and the length of my disk is dx, so I multiplied by dx. Now I can say that the moment of inertia of a disk about its diameter, because here I'll have to find out your AB. Guys, can you please see the figure? AB is the diameter. So here you will have to find out the moment of inertia of the disk about the diameter. You will have to find out about AB means you will have to find out about diameter. So I can say that moment of inertia of the disk about its diameter is given by the formula mass into radius square upon 4. We derive this equation that moment of inertia of the disk about the diameter is this. So therefore I can say that moment of inertia of the elementary disk, about its diameter AB will be nothing but mass. Now mass of the elementary diameter disk we found out is m upon L dx into radius is going to be nothing but r square by 4. Right? Now by applying theorem of parallel axis, if I apply theorem of parallel axis, then moment of inertia about the axis y-o y-bar. Guys, can you please see this? This is my y-o y-bar. Y-o y-bar and the diameter are parallel to each other. Therefore, I apply theorem of parallel axis. So, by applying theorem of parallel axis, moment of inertia of the disk about y-o y-bar will be nothing but I-O is equal to IC plus MR square. So in that case, this will be m upon L dx into R square by 4. That is IC plus M. That is m upon L dx into R square. The distance is x square. Right? Moment of inertia about any axis is equal to moment of inertia about the parallel axis plus mass into the square of the distance between them. So therefore this is going to be the moment of inertia of the disc about YO Y bar. Now I can say that I can use this to find out the moment of inertia for the entire disc. I can say that moment of inertia of the cylinder about YO Y bar can be obtained. I found out moment of inertia of the disc, and we said that the cylinder is nothing but multiple discs stacked one upon the other. So if I integrate the moment of inertia of the disc, I'll get the moment of inertia of the cylinder. So I can say moment of inertia of the cylinder about YO Y bar can be obtained by integrating the expression between the limits x is equal to 0 and x is equal to L by 2. Guys, if can you see the diagram? The entire length is L. That means this length from here to here has to be L by 2. This will give me all the discs on one side of YO Y bar. Then to find the whole cylinder, all I have to do is multiply that answer by 2. By integrating this, I will come to know all the discs which are on one side of axis YO Y bar. And then double that for answer, right? So therefore,
so then why don't we take L directly?
Because if I am assuming this to be the origin, the total length on one side is L by 2, no? Right? By integrating the expression between the limits x is equal to 0 and x is equal to L by 2 and multiplying the result by 2, therefore I can say moment of inertia will be twice integral of 0 to L by 2. We found out of the disk m upon L dx into r square by 4 plus m upon L dx x square. Right? Now here I can say that m upon L can be taken common, so twice m upon L integral of 0 to L by 2 r square by 4 dx plus x square dx. Right? Split the integral. So in that case this is going to be nothing but 2m upon L integral of 0 to L by 2 r square by 4 dx plus integral of 0 to L by 2 x square dx. Whatever is constant comes outside the integral, so this is 2m by L r square by 4 integral of 0 to L by 2 dx plus integral of 0 to L by 2 x square dx. This is 2m by L r square by 4 integral of dx is nothing but x when the limits are between 0 to L by 2 plus integral of x square is nothing but x cube by 3 when the limits are between 0 to L by 2. This is 2m by L r square by 4. How do you solve the limits? Upper limit minus lower limit. So this is L by 2 minus 0 plus 1 by 3 L cube by 8 minus 0. Right? So in that case you will get 2m by L r square L by 8 plus L cube by 24. Here I could take L common and 8 common, so you will get 2m by L. I am taking L by 8 common, so you will get r square plus L square by 3. L and L gets cancelled. This is 4, so this is m by 4 r square plus L square by 3. Right? So therefore I could say that this is nothing but m r square by 4 plus l square by 12. That is going to be my moment of inertia of a cylinder about an axis passing through the center and perpendicular to the cylinder. Right? Now, once I know this, I can find out the radius of gyration. Radius of gyration K is given by the formula square root of I by m. I you just found out is this, so this is going to be nothing but square root of m r square by 4 plus l square by 12 upon m. M and m gets cancelled, so this is going to be square root of r square by 4 plus l square by 12. That is going to be my radius of gyration. So this is how you find out the moment of inertia of a cylinder about an axis passing through the center and perpendicular to the cylinder. Now let's try to find out moment of inertia of the cylinder about an axis tangent and parallel to the cylinder, to the cylindrical symmetry. See, about a tangent parallel to its axis of cylindrical symmetry. Meaning, see, this is how this is going to be. This is my cylinder. Right? This is my axis of cylindrical symmetry. I want to find out moment of inertia about a tangent parallel to this axis. That means I want to find out moment of inertia here about this axis. Let's call this axis as IC. Let's call this axis as IO. We know that the distance between them is going to be R. Right? So I can say that moment of inertia of a solid cylinder of mass m, moment of inertia of a solid cylinder of mass m and radius r about its own axis, of cylindrical symmetry is mr square by 2. That's the first thing that we did, because this is nothing but a disk and moment of inertia of the disk is nothing but mr square by 2. Now I can say, by since these two axes are parallel to each other, I can say by theorem of parallel axis, if I apply theorem of parallel axis, I can say that the moment of inertia of the cylinder, about a tangent parallel to its own axis will be nothing but IO is nothing but IC plus mr square. That's my normal formula of theorem of parallel axis. This is nothing but mr square by 4. IC we just found out is mr square by 2, plus mr square. So this is going to be nothing but 3 mr square by 2. That will be my moment of inertia. Next, let's find out the radius of gyration. Radius of gyration K is given by the formula square root of I upon m. So this is going to be nothing but square root of 3 upon 2 mr square upon m. So this is going to be root 3 by 2 into r. That will be my radius of gyration. Right? Next, let's try to find out the moment of inertia of a solid sphere. This was cylinder. Let's try to find out moment of inertia of a solid sphere. Moment of inertia of a solid sphere. Right? First, let's try to find out about its diameter. Moment of inertia of a solid sphere about the diameter. Now let's consider a solid sphere of mass m and radius r. Consider a solid sphere of mass m and radius r rotating about an axis, rotating about an axis coinciding with its diameter. So in which case I can say that the volume of sphere V is 4 upon 3 pi r cube. Volume of the sphere is this. In that case I can say what will be the mass per unit volume. Mass per unit volume will be nothing but m upon v, so which is going to be nothing but 3m upon 4 pi r cube. That will be my mass per unit volume. Now let us consider, if I have a solid sphere, let us consider that I take a thin slice of the solid sphere. I have a solid sphere, right? This is the diameter, right? Let us take a thin slice of this solid sphere. I'm taking a thin slice of this solid sphere. Okay, let's assume that O is the center, AB is the diameter, this is my radius. Let's consider a thin slice of the sphere at a distance of x from the center, right? Now I can say that consider a thin slice of thickness dx. Let's assume that this thickness is dx. Let's assume that the thickness of the slice is dx at a distance of x from the center of the sphere. Now if I apply Pythagoras theorem, I can say that the radius of the slice will be nothing but square root of r square minus x square by Pythagoras theorem, right? So once I know the radius of the slice, I can find out the surface area of the slice. Surface area is nothing but pi r square, so this is pi, and we've just found out that the radius of the slice is r square minus x square. I can also find out the volume of the slice. Yes. So we also the surface area. If I'm looking at the slice from a top view, what do I see? Circle. If I'm looking at a slice from the top view, what do I see? A circle. And what's the area of a circle?
Pi r square. So it's a square over there.
Pi r square. Okay. Now volume of the slice. Volume of the slice is nothing but area into the height. So area we found out is pi r square minus x square into height. That is going to be my dx. We said that the thickness of the slice is dx. In that case, what will be the mass of the slice? Mass of the slice is nothing but volume into density. Volume you just found out is pi r square minus x square into dx. Density you had already found out before. Remember, we had found out mass per unit volume. Mass per unit volume is nothing but density, which we had found out as 3m upon 4 pi r cube. 3m upon 4 pi r cube. So that is going to be my mass of the slice. Okay. Once I know the mass of the slice, I can find out the moment of inertia of the slice. Moment of inertia of the slice about an axis passing through its center. Passing through its center and perpendicular to its plane. Will be nothing but, it will be the same as moment of inertia of a disk about an axis passing through the center. So in that case, it will be nothing but mass into radius square by 2. Right? Mass of the slice you just found out is nothing but pi r square minus x square into dx into 3m upon 4 pi r cube. This is mass into radius square, right? Radius square upon 2. Radius of the slice we had already found out is nothing but r square minus x square under root. So square will be r square minus x square upon 2. Now pi and pi would get cancelled, right? So in that case you will get this as 3m r square minus x square the whole square dx upon 8 r cube. Right? So once I know the moment of inertia of the slice about an axis passing through its center, then I can say that moment of inertia of the whole sphere about AB, moment of inertia of the whole sphere about AB, moment of inertia of the whole sphere about AB can be obtained by integrating the above expression, because I can say that the whole sphere is can be considered to be made up of multiple slices joined together. So moment of inertia of the whole sphere about AB can be obtained by integrating the above expression between limits x is equal to 0. I'm going to move on one side, and x is equal to r. That means if I move from 0, that is from the center to the one end of the circle, that is one end of the sphere, it will be the radius, and then multiplying it by 2 because I have it on both the sides, and multiplying the result by 2, right? So in which case I can say I is nothing but integral of 0 to r 3m r square minus x square dx upon 8 r cube and multiplying the result by 2 whole square, right? And then multiplying the result by 2. Now whatever is constant will come out, so this is going to be nothing but 2 into 3m upon 8 r cube, radius cannot change, integral of 0 to r square minus x square the whole square dx, right? Now expand this, so this is going to be nothing but 3m upon 4r cube 0 to r. This is in the form a minus b the whole square, so this is going to be equal to this is a minus b the whole square, so this is going to be a square minus 2ab plus b square dx, right? Split the integral, so this is going to be nothing but 3m upon 4r cube integral of 0 to r raised to 4 dx minus integral of 0 to r 2r square x square dx plus integral of 0 to r x raised to 4 dx, right? Whatever is constant will come outside the integral, so in that case this is going to be nothing but 3m upon 4r cube r raised to 4 integral of 0 to r dx minus 2r square integral of 0 to r x square dx plus integral of 0 to r x raised to 4 dx, right? So in that case this can be written as 3m upon 4r cube, this is r raised to 4, integral of dx is nothing but x when the limits are between 0 to r minus 2r square x square is nothing but x cube by 3 when the limits are between 0 to r plus x raised to 4 is x raised to 5 upon 5 when the limits are between 0 to r. How do I solve the limits? It is upper limit minus lower limit. So this is going to be nothing but 3m upon 4r cube. This is r raised to 4 r minus 0 minus 2r square by 3 r cube minus 0 plus r raised to 5 minus 0 upon 5. This can be written as 3m upon 4r cube. This is r raised to 5 minus 2 upon 3 r raised to 5 plus r raised to 5 upon 5, right? R raised to 5 comes out, so this is 3m upon 4r cube into r raised to 5, 1 minus 2 by 3 plus 1 upon 5. This is going to be nothing but 3 mr square by 4 into 15 is the common denominator, so 15 minus 10 plus 3. So in that case this is going to be nothing but 3 mr square by 4. This is 8 by 15. So this is 1s are 5s are 2s are. This is 2 upon 5 mr square. So that is going to be my moment of inertia of a solid sphere about its diameter. Right? Do we get this thing clear? Now once I know the moment of inertia, then I can find out the radius of gyration. I can say that the radius of gyration k is nothing but square root of I upon m. So this is square root of 2 upon 5 mr square upon m. Therefore k is going to be nothing but square root of 2 upon 5 into r. That is going to be my radius of gyration. So this is my moment of inertia of a solid sphere about its diameter. Fine, do we get this thing here? Now let's try to find out about a tangent. About a tangent. How do I find out the moment of inertia of a solid sphere about a tangent? Right? Let's try to see this. Solid sphere, right? This is my axis passing through the center. I want to find out the moment of inertia about an axis passing through the tangent. Now we know that the distance between them is going to be r, right? So let's consider the point of contact to be O, right? So I can say that the moment of inertia of a sphere about its tangent, moment of inertia of the sphere about its tangent can easily be obtained by using theorem of parallel axis, can be obtained by using theorem of parallel axis, right? In which case I can say that IO is equal to IC plus MR square, right? Where I can say that IO is the moment of inertia of the sphere about the tangent and IC is the moment of inertia of the sphere about the diameter, where IO is moment of inertia of the sphere about a tangent and IC sorry, is moment of inertia of sphere about diameter, right? So in which case I could say that IO is equal to IC. IC we just found out about the diameter. We found out is nothing but 2 upon 5 mr square plus mr square. So this is going to be 7 upon 5 mr square. That will be my moment of inertia of the sphere about its tangent. Now in that case, what will be the radius of gyration? Radius of gyration k is going to be square root of I upon m. So this is going to be square root of 7 upon 5 mr square upon m, that is square root of 7 upon 5 into r. That is going to be my radius of gyration, right? Okay, we will stop this here for the day. Thank you very much.